And we are live. Thank you, everybody, for the next community workshop. This is a workshop series where devs from community inside Developer DAO showcase their skills, get us to level up a little bit more, and we just get better, right? So very happy to have Crypto on board. Crypto, for those that don't know, I would say when the DAO was making changes from season 1, season 2, and a lot of people were coming and going, I think Crypto was kind of the champion of VC5 at the time, hanging out, sharing screens, helping people. He's hardcore Solidity dev, hardcore in getting into Rust. So like he's kind of been the go-to person to ask questions. He's always super, super helpful. So a really, really big pleasure to bring Crypto on board. He's also working on Raisin Labs. That might be a sub DAO for the DAO. It is a fundraising kind of platform with a little bit of a twist. But I'm going to go ahead and let Crypto take the show because we are here for Rust. And let's see what's up. What's up, Crypto?
Hey, what's up, Billy? Thank you so much for having me today. I'm very excited to discuss the foundations of the Rust programming language. A quick little addendum before we start. This will not be oriented towards smart contract engineering. So I'm teaching you idiomatic Rust right now, not for Solana, Near, any of the domain-specific languages, which all are wonderful in their own ways, but we're getting the real thing up front, off-chain.
Very cool. Very cool. So the obviously, Rust is like a big thing in the space right now. Like I get all the time, like, do you know Rust? Are you familiar with Rust? Like we're again, like you said, you have Solana, Near, Polkadot, a lot of these other chains, not EVM. Even EVM is coming into the Rust game a little bit. But seems like it's the new language to learn to be, I don't want to say relevant, but to be in demand in the near coming future, right? Like it just seems like it's another skill to have that is really good to have in your arsenal of languages.
100%, especially if you're building mission critical infrastructure off chain or even blockchains themselves, right? Those are pieces of mission critical infrastructure.
Yeah, definitely.
But yeah, it's really great to see Rust getting a lot of hype in the spotlight. And thankfully, I think Rust actually kind of lives up to that hype. There is a bit of a learning curve, of course. Many languages have unique features, but Rust is fairly unlike many of them with things such as the borrow checker. It will be a little frustrating at first. It took me a while personally to write good production code. And, unfortunately, we can't get to every single nuance within the course of an hour, but I hope to give everyone a bird's eye view of the most important concepts in Rust when you're starting out.
Very cool. Yeah, I remember when I started with Rust, and I'm not saying I'm very good at it, but ownership and then losing ownership was a concept that took me a little while to click in from time to time. So definitely go for it, Crypto. Take the show.
Beautiful. All right, on to our first real slide. So why Rust? Why is it unique? Why do you care? Why should you care? So Rust, of course, made a massive splash in the blockchain ecosystem with Polkadot, Near, Solana, among other layer ones, bringing it definitely straight into the conscious of our industry. But outside of blockchain and Web3, some of the largest companies in tech currently are adopters of the Rust programming language. So Amazon, IBM, Facebook, even NPM even have Rust running on your computer with VS Code and Discord. The best part is it runs absolutely everywhere. Either you can put it on the web, in embedded context and embedded electronics, bare metal without any operating system. So it's highly flexible, highly powerful. Better yet, we have these things called zero cost abstractions. And so when we use higher level syntax in the Rust programming language, we do not actually incur any runtime cost for using these beautiful abstractions. So things like generics, collections, iterators, they'll add to your compile time, but it won't actually make your software run any slower. Another thing I love about Rust is that the compiler is absolutely your best friend. It will literally teach you how to write Rust code at times when you mess up. Relatedly, Errors can also be efficiently propagated across the stack, even if your 6 libraries deep, and provide you useful information to hopefully fix the problem or let the devs know how to fix it. There are a couple things we won't be discussing, like macros and concurrency, some more difficult topics in Rust, but as you progress in your journey, you will definitely come across these. One recommendation I have is the Little Book of Macros, and Maria Boss wrote a really fantastic book on locks and concurrency in Rust. Just a couple recommendations when you get to that. So what else? Well, we got the borrow checker, and the borrow checker is the magic that enforces ownership rules at runtime. So basically, it'll prevent you from writing bad code that does stuff like leak memory unintentionally. Now, you can leak memory in Rust using stuff like box leak, but you're not going to do it unwittingly. There's no way to accidentally do something like that. And so there's a system of ownership in Rust where basically this takes the place of the garbage collector in terms of cleaning up memory. Rust type system is also really powerful, extremely strict. This is something that tilts beginners fairly commonly, but it comes with really great benefits. So on enums, we have cool stuff like algebraic pattern matching, where the compiler will enforce that you have managed to cover all the cases from the enum, and type inference. So, there are many times in Rust where you actually don't even need to explicitly annotate your variable. The compiler will actually be able to simply infer it at times from the literal you provided or from the types being piped through your code. Another thing I love about Rust, we have functional idioms like iterators and closures and monadic error handling. If you don't know what monadic error handling is, we're going to talk about that a little bit more in depth later. But the gist of it is that we have these enums called option and result. And basically, we can choose how we handle these specific errors depending on the different cases we get. And so this is actually something else that we could use our algebraic pattern matching with.
Got it. Crypto, to cut you in on there, just, I hear a lot of people that try Rust that are, I think, primarily more JavaScript like developers. They really have a hard time, doing that transition or understanding or getting started on it. And, I know that you're mentioning memory leaks and ownership. And I know one of the biggest issues with JavaScript is, being able to change, a non-type variable into something like an int to a string to a Boolean on the fly, right? So like those kind of concepts are tough because then you have to type, state the type that it is at the time. And then it gets a little bit deeper from there. Is that like, is there like a good path to go in that aspect?
For me, at least, Rust was a lot like relearning how to reason about my code. If someone isn't used to a type system, it's the sort of band-aid that we have to rip off instantly. It makes you understand what exactly is going through your code and when. Rust type system can also be a little confusing too at times. We have like 3 different ways we could express a string. Char, which is like a single character, string slice, which is an unowned string, and then you have the owned version, which is just a string. So people are going to have to get really comfortable with types here and understand how values are being piped through their code. The last thing I'll briefly mention, again, it's macros, and macros, this is Rust code that writes more Rust code. It is absolute witchcraft. It's very cool, and can massively reduce boilerplate in your production code. But that is a whole lecture of its own, but an incredible feature of the Rust programming language. All right, values, pointers, and references. So whenever we deal with a value in Rust, it has 2 very important things that are inseparable. You have the type and you have the element. And the element exists such that it satisfies the type. So let's say we have an unsigned integer of 128 bits. So the type is an unsigned integer of 128 bits, and the element, say, is 5. We also have many pointers in Rust, but we have beautiful abstractions, so it doesn't get really weird to handle. Simply, pointers are values that hold an address to a region of memory. So you can imagine that we have stored that U128 in storage, and we can go ahead and we can actually establish a reference to that value with a pointer. And so pointers themselves are not the underlying values, they just point to that location. It references that exact location in memory. And we have, likewise, an important interaction with references and pointers. If we use an asterisk on a pointer, we can actually retrieve the underlying value. So a lot of Rust is juggling memory, values, and pointers.
So quick question for you on that one, Crypto. Just to kind of compare it to a Solidity example. Let's say we have a uint 256, right? Value 5, right? And so now we're getting in the lower level of kind of pushing the value in a certain memory stack location. Let's say it's in an array, right? Like when we compile our contract, and then that value that we set, in our contract now gets set into array position 0 for right now, just for an example. And so now there's a reference saying, okay, that uint 256 that's valued at 5 is now in this memory location in this memory array at 0 point. And now we have a reference value saying, okay, at the array and at position 0, we have our uint 256 value 5, right? Is this pretty much what it's handling?
Yes, but it looks a little different. So we're in Solidity in the EVM context. Contract storage just is a contiguous array of bytes. But in the Rust programming language, when we are targeting our computer, we have two important locations in memory. We have the stack. You might remember that from Solidity. It has a LIFO stack of 1024 depth. And then we have the heap, which we don't have in Solidity or the EVM. And the heap is kind of interesting, right? So it doesn't matter in Rust whether or not something is sized to be on the heap, but it needs to be statically sized and known at compile time if it wants to be on the stack. And there's a really important trade-off here because the stack is a much quicker region of memory than the heap is. When we refer to something on the heap too, we point to an address in memory, and it doesn't matter whether or not it grows or contracts, that address in memory will still remain the same. But on the stack, we need to explicitly know the type if it is to be placed there.
Got it. Okay, cool, awesome.
The other important semantic I'm going to mention is that the most common pointer in Rust is a reference. So it's that ampersand. Every time you use this ampersand, you create a pointer to a value in memory. Let me see if there's anything else interesting in my speaker notes here. Oh, yes, here we go. So there's a very special semantic with references, of course, and it has to do with the system of ownership. So let's say you don't want to take possession of a value. So if you take possession of a value, the line after it will be out of scope completely. You cannot use the original name to reference it, but the bits most likely will still be there in some literal sense, but you can access them without causing problems.
Right. For those that haven't don't know what scope is when you're going down the Rust code, right? You have these little subsections, and if something's referenced somewhere else and then you go into the subsection, it no longer is referenced. It's you can go to another section and they won't know that each other exist. So you have these little, I don't know what the good way to explain it on that, these scopes are these own little piece snippets of code that don't know that they are even existing next to each other, and so they don't know what the values are or anything in that in each scope is, right? Would that be kind of the simple down version of that one, Crypto?
Yeah. You can kind of almost reduce it down to kind of like being its own little context, and these little contexts usually are within a function, or they could just even be main. You could have multiple blocks with curly braces. This is how we express scopes in Rust.
Yeah. I mean, for me, like when I was forced to learn JavaScript, like I pretty much did like my entire code one single page and one line. So if you're trying to do the same thing in Rust, like obviously it's not going to work out very well for you out there. So you can understand the struggles. But go on, Crypto, go for it.
100%. And the nice thing too about JavaScript and a lot of other like higher level languages is that they'll like clean up memory for you. They're like your personal made, a program that like runs with your compiler to basically just clean up after you. But not in Rust. It's non-garbage collected, and of course we get some additional runtime benefits because of that. So continuing on, if you don't take ownership of some value, you are either mutably or immutably borrowing the value. So there's also a special rule with mutable borrows versus immutable borrows. And so you can have as many immutable borrows as you want, but you can only have a single mutable borrow. And this is because if we have multiple mutable borrows out, it lets us mutate the underlying value. And if multiple writers are trying to mutate the same exact place in memory, it creates what we call a race condition, and that is not good.
I'm gonna break that down a bit because that really actually took me a long time to understand as well. Like you have this one value that's set in a memory location, like this is the point of reference, right? And so you can't have, well, for memory optimization, right? This is how I understand it, is like it's kind of pointless to have the same copy of it in multiple locations. So this is one true immutable point of value, and then you have these references that then use that value, right? And that's when it comes down to the ownership, right? Because if you give the value away, then the new variable owns it in a sense. So like it's just constantly pointing to this one specific point of truth. And so instead of having 10 copies of that same value throughout the memory, it's more memory efficient to do that, because then you can just point to this one single point. And then if you give that away and all the pointers are pointing to the place that's been given away, I know I'm bad with a camera, then it just basically breaks the whole system. Is that kind of close?
You're close. You're in the neighborhood. Yeah. So race conditions are things that create what we call undefined behavior. And undefined behavior can lead to potentially even security issues. But you got it right in the sense that, so we have this original variable that has its location in memory, right? And anytime we take a reference to it, we're referring to that specific location in memory, even if we take out 100 immutable references. But weird stuff starts happening as soon as we take out multiple immutable borrows. And that is one important rule we cannot violate if we want to prevent race conditions in our code. That means multiple writers trying to access the same piece of data immutably, basically trying to change it.
Got it. Again, ask questions in the chat, guys. I know this is like Rust can be kind of scary in the beginning, and then understanding these concepts on something like, but go ask questions, guys, because Crypto is the man for answering these things. Go on, Crypto, go on.
Beautiful. Plus, I'm also going to bring this up later in the presentation as well. I'm going to go a lot deeper into ownership, but I'm just kind of getting everyone prepared for what lays directly ahead. The one last note I'll make here is that Rust static type system will forbid you from making a dangling reference. So basically, after a value in memory has already been freed and you try to reference it after the fact, the Rust compiler will not let you even compile your code. And now we finally get closer to code. So these are our scalar types in Rust. Scalar basically just means really elementary. So we have signed integers, unsigned integers, floating point numbers, which are just decimals, strings, characters, and booleans. And so the important difference between signed and unsigned is that signed integers can be negative, unsigned cannot. Floating point numbers are decimals, string slice is actually just a small collection of characters, and we can make the heap allocated string from the string slice. And then lastly, the Boolean values that can be true or false. One brief thing that I will actually note about strings here, you can directly create a byte string if you prefix B to the double quotes. One more thing, sizing. So I mentioned before that stack allocated items, they need to be known at compile time, their size. And so an I8 is 8 bits wide, an I16 is 16 bits wide, and so on and so forth. So they're always n bits wide, and I size and U size will always be the width of the pointer. All right, we finally have our first examples here. So we can assign variables in Rust with let, and we use snake case primarily as the convention. If we use a constant value, then we use what's called screaming snake case, which is just snake case in caps. So our first signed integer is 123, an unsigned integer of 420. Notice how I explicitly annotated the types here. The thing is in this case that both of these values can either be an unsigned integer or a signed integer, so I have to explicitly tell the compiler what I want. Below is actually an example of type inference. We have a negative value here, and before I mentioned that signed integers cannot be negative, and so unsigned cannot be negative. And because we have a negative integer here, the Rust compiler is able to validly infer its type because it could be no other. And I gave a few more examples here of a float, a Boolean, and hello world, which is a string slice.
Crypto, I'm going to jump in here too. For those that are kind of playing around with Rust and that use CoPilot, CoPilot will automatically suggest the I32 option on there. And then just for the byte size, right? Like I think when you go I8, that goes up to 8 to the power of 8, right? Like it's the max is.
No, it's not weird like that. So 8 bits, but alignment could be weird.
Got it. Okay. So like it is similar to like what you would do, like someone familiar with Solidity would be that same range, except everything's unsigned, right? Instead of like being able to go negative. It's just they're using that space for more of a positive, like double the size of the maximum number you can choose. And then when you have the signed integer, you can go like, let's say to 64 and negative 64 versus just being able to go all the way up to 128, right? So you can only go from 0 to 128. And then if you're using the ability to go negative, you can go only from positive 64 to negative 64. So choosing your sizes before that is what you, when you have your signed cases, right? Or your unsigned cases when you declare it in the very, very beginning.
I think in many cases, Rust will just default to I or U32 unless the size of the actual literal value is larger than the size those bits can store. This isn't actually GitHub CoPilot's magic. This is Rust's LSP, a language server protocol, which fills in for this. TypeScript has one as well, but I think Rust's LSP is really overpowered and actually makes the developer experience much more enjoyable.
I didn't know. I thought it was the magic of CoPilot, so props to Rust.
All right, now we're on to compound types. We graduated from scalar types, so now we can turn up the heat ever so slightly. So we can make compound types of our scalar types. So we got two types here. We have arrays and tuples. Both are allocated on the stack. So arrays can have a generic type. So this is a foreign concept if you're not very used to type systems. Generics can effectively be any value, and you can place certain restrictions on those traits, as we'll find out later. So just think of T for now as an arbitrary type. And then N is the size, so it could be 4, it could be 400, but because it's known at compile time, you can throw it on the stack. Now, also, another thing I'll note is that arrays will have a homogeneous type, while tuples could be heterogeneous. So in other words, we can have a bunch of different types inside of tuples, but arrays have to all be the same exact type. Every element. Okay, that's all I have for that slide. Let's go on to some examples. So here's our most basic array. It is of type i32, and it has 3 elements, 0, 1, and 2. That is how we index them. I give a really similar example for the tuple. We have 3 i32s, which we have to explicitly annotate because they could be otherwise. So let's... Oh, what's
when
up,
you,
I heard you.
Oh, sorry to interrupt. So when you say explicitly annotate, can you go a little bit deeper into that one? Because I see the i32s, and then I see the ampersand with the basic tuple in the tuple array.
Yes. So the reason you're seeing 3 i32s here is because these i32s could be strings or any other type. It doesn't matter what types you have as long as you annotate them inside of the tuple. But you can't do this with arrays. So you're going to be stuck with i32 for all of your elements here, but these could be completely different, right? You can have an i128. You can have a floating point number in there too. So we annotate for each of the positions.
Got it.
And so let's start combining things in weird ways already, because I know you guys like that. So I mentioned before that we have these weird things called references, and I used 3 of them here. So I am borrowing a reference, so I'm referencing the same exact area of memory immutably 3 times, and that is okay. We can have as many immutable borrows as we want, so I just did it thrice. So we have 3 references to basic tuple, all in its own position. So we have an array of tuples with 3 i32s in them.
So just to recap that basic tuple is that first position 0 is 0, 1, 0, 1, 2. And then the next one over, position 1, is again another copy of 0, 1, 2. And so we have an array of arrays in layman's term.
Exactly.
Mm-hmm.
Exactly.
Cool.
I don't know why I named this one response, but I just wanted to show you how we could access this weird object, right? So we can access basic tuple array by index. So that's what we do with the square brackets here. And then with the dot syntax, we can access one of the members of the tuple. So we are accessing the 3rd member of the tuple, namely the number 3. I just gave some extra examples of some of my favorite athletes here, some mixed type action here. So we have a name and we have a number. That's usually what athletes got. So athlete.0 is Josh Allen's name, and then athlete.1 is Josh Allen's number, 17, go Bills. Then we can make an array of athletes, kind of just doing the same thing as before, exactly how you would expect, but this time it's just explicitly, and I put it in there explicitly instead of taking references to the information.
Got it. I don't see Billy Jitsu's name on there, so I know something's wrong with the compiler. But question from Nate. He's like, what is the ampersand for in front of the i32s?
Oh, so this here, very good. So this basically tells us that we want this type to be borrowed, not just a regular tuple. So this allows us to not take ownership of basic tuple when we are referencing it on the right-hand side of the assignment.
And that's basically going back to ownership, right? Overly, like we don't want to take over the actual type on this new array. We want to just reference it, right? Like we don't want to move it.
Yeah, exactly. In this instance, it's just an example, so it doesn't matter too much. But there are plenty of situations in which you will consciously choose not to take ownership because you want to reuse that value at a later point in your code. And so, in other words, I can access basic tuple after it's been referenced 3 times in basic tuple array because I didn't take ownership of it. But if, say, I removed the ampersand on the first basic tuple here on the right-hand side of the assignment, then I would actually get an error here, basically saying that, hey, I just moved it. What are you doing? You can't use after free. And here we come to our functions and methods. So we can declare a function with the keyword fn. Arguments can decide to take an ownership or a reference to the value, depending on what you need, of course. You can return values in the function signature with this arrow. And functions associated with types are called methods. We're going to talk a lot more about structs and enums, but just know for now that an associated function is called a method. So a couple of fun examples here. One function, one method, they're pretty much the same, but I made them slightly different. So odd or even will simply print out whether or not you have an odd or even number. It'll take a U8 as an argument to the first function, calling it number. Also keep in mind that number, of course, implements a trait called copy. It is a scalar value, and so there's actually a little sorcery where it isn't as affected by moves as, say, something heap allocated, like a string. We can literally copy the bits when we have a scalar type that implements copy. Over here on the right-hand side, we have our very first enum. Welcome to enums. Enums are fantastic in Rust. You can associate values, do all sorts of cool stuff. But in this case, we're just representing two potential states, even and odd. And so same code as before, but I'm just returning one of these enum values. And the way we access enum values or associated functions to structures or enums, we use this double colon syntax. Oh yeah. Also, we have a little piece of control flow here in Rust. If statements. We don't need to surround anything in parentheses. We just open the blocks and create a new scope. One other thing I'll mention, because we're here, we have an implementation statement, and so you can implement your types to add specified behaviors or ways that you want this type to behave. So you can add various functions, constructors, type builder patterns. This is taking the place of something like classes in JavaScript and Python. But we're going to hear a lot more about this soon. Back to memory. I know we briefly discussed this in the beginning, but you deserve to know more about the stack and the heap. So sizes are fixed and must be known at compile time. It is much quicker. Easy to manage the stack. Locality in memory. Okay, this is an interesting one. So what we mean by locality in memory is that if you access two completely disparate pieces of memory, it's not going to be very fast compared to, say, doing something like accessing the same exact piece of memory twice. And the reason for this is because we have something in our hardware called caches. And so when you recently visit a location, it'll end up in one of your L caches. And if your cache memory is much quicker than the rest of the memory on your computer, and so if you're allocating on the stack, there's a much higher chance that you're going to get a hit in your cache to retrieve this data quicker than you would be on the heap, where you might not have this extra benefit of speed.
Just to clear up on that, like in a real life example, let's say you came home from the club, right, and you were, or in 100% there, and you took off your shoes at random locations, right, and it's morning time, and you found one shoe, but then you have to search around your house for the other shoe. That's kind of like memory allocation, right? Like ideally they'll all be kind of lined up where they're supposed to be, but if you have one shoe here, cool, and then you have to look around for like your whole house for the other shoe because you don't know where you left it, that's basically what locality is, right? Like it bulks everything together for faster, retrieval in a sense. Like it knows where everything is kind of laid out in a sense.
Exactly. Yes,
Yeah.
that is a really good example. And sounds like a really rough night.
Yeah.
But yeah, also like the other nice thing, say we're working with something like an array, right? An array will have the homogeneous type, and we will be able to basically predict how much memory we need to allocate between each contiguous piece of memory in the array, making up the elements. And so being able to predict this makes it much quicker.
Real quick question from Terja. He's going to, this is a good question. Like for keeping in mind, like, is it important to keep in mind the heap and memory when building programs? Or does it do it for you is kind of the question.
So you need to keep it in mind, but it will mostly do it for you. It's really as simple as using different types, and a lot of these dynamically sized types will either be traits or they will simply be heap allocated. So
Awesome.
if we don't know the size of compile time, it's on the heap and it's going to be slower. But most of the time, you don't have to think too hard about where it's going. But if you're trying to optimize your code, you're going to think a lot about the stack and the heap. Let's see if I have anything else here that I want to mention. Oh yeah, the Rust compiler is also really, really conservative. So it would rather reject some valid programs than allow any possibility of you unintentionally leaking memory. And so some people love this, other people hate it, but we have a subset of Rust to kind of deal with these cases, and this is what we call unsafe Rust. This will be also outside the scope of this lecture, but it is an important subset, or more important subset, when you're dealing with things like bare metal or no standard library. And here we come to the rules of ownership. I've been teasing it for a long time. We're finally here. The borrow checker greatly influences the ergonomics of how Rust code is written, and it is responsible for enforcing the rules of ownership. We will define a value as moved if and only if another variable or function took ownership of it. We can take so-called references to values that we don't want to move, and the same applies to function arguments. So, 3 rules really explicitly. Every value is owned by something. It can own itself, it can be owned by a variable, it can be owned by a function, but it is owned by something. Each value only has one owner only one owner at a time. I should have put an asterisk here because this is mostly true, but we have some interesting smart pointers like reference counters and atomic reference counters that can basically express multiple owners for the same piece of data. But of course, there are interesting rules and caveats introduced as a result. When a value goes out of scope, it is completely dropped from memory, never to be seen again. And we have a really basic example here of me violating the rules of ownership. This is also the first example of the compiler being absolutely incredible. So let's start. We have a string called A. We're using the associated method from onString from the standard library, and we are passing it a string literal called hello world. The variable B will go ahead and take ownership of this string, and then afterwards we tried to reference A by calling the println macro on it. So println is kind of like console.log in JavaScript. It just prints to the console, but it is a macro, a function-like macro, in fact, and makes your life very much easier. This is one way to express the syntax for println internally. The other way to do it is you'd have those closed brackets, and then you'd have a comma after the quotation marks, and then the interpolate the value you want to pass in. The These curly braces will be interpolated by position if you have multiple of them. Okay, so here's our compiler. It's saying that, hey, you messed up, bud. String doesn't implement copy. What are you doing? And we moved the value in line 7. And so not only did it give me an error, but it went ahead, it was really nice, and it actually gave me a suggestion on how to fix the code. If we add .clone to line 7, where we are taking ownership of A, we can clone it on the heap and use it later instead. Instead of just taking regular ownership, we'll just take a clone of it instead.
Question, Crypto, before we go on to the next one, right? So just to recap, right, we have this A variable here, and we set B. So basically, for being memory efficient, it just literally moves the value over to this location, and A no longer exists theoretically in the memory.
Exactly.
And so, and then on that point, if we wanted to, like, maybe make a clone and use the heap, we could also create a reference point, right? So we can have B as a reference would have the ampersand as well, right? So it would be ampersand A, and then B would be that reference point to A as well.
Super close. Sorry, I have to split a couple of hairs here, Billy.
Got it. No worries.
So string is a type that is allocated on the heap already. So if we take a reference to A, we'll be all good. Like, that is an acceptable thing to do. But it won't. It will also be allocated in the same way.
Got it.
Well, actually, it'll just be a pointer. You're not really allocating new memory necessarily.
No. But it's because of the memory efficiency in Rust is why you can't do that, right? Like you can't just keep making copies and copies unless you specifically say so to be used in the heap. But because it wants to avoid all that kind of memory bloat, it's why it moves the variable. It's kind of like the point of Rust, or like the whole language in a sense.
Right. Yeah, you're very much on point there. The reason why Rust has these rules of ownership is because we don't have our memory cleaned up automatically after us with something called a garbage collector. Now, Golang is garbage collected, JavaScript is garbage collected, so is Python, a lot of modern languages, but some of the older languages that Rust is trying to replace, like C++, is also imperative and just imperative. That doesn't matter. It doesn't have a garbage collector either, but you're forced to manually manage this piece of memory.
Yeah.
And not screw up.
I'm just gonna put a note out there that I can hear your New York when you say garbage, like coffee. That's the only time I hear the true New Yorker in you. Anyways, go on, Crypto, go on.
I love it. But yeah, it's because we're not using a garbage collected language. Also keep in mind, clone is the more expensive counterpart of copy. Copy is implicit, but clone needs to be explicit because we have a runtime cost for that. And yeah, okay, cool. I covered everything on this slide. We have one more beautiful example, slightly more complicated, but functions, of course, can decide whether or not they want to take ownership. So in our first example here, we have a string being used as the argument type for name inside of greeter. And so when we call string from on the string literal Crypdough, we are taking ownership with greeter, and we cannot afterwards access my name. But in the next slide, we make it slightly different. String slice is a scalar type, if you remember. We're taking a string slice instead of a regular heap allocated string. We're passing it to my greeter. We are changing the name because we can do that. We can access it. It is scalar, and we only took a reference and inside of this function. So I'm again able to mutate this original value because we have mute here, let mute my name. And then we change it to Satoshi Nakamoto and then call greeter again. So whenever you want to mutate a value in Rust, keep in mind too that you need to use the keyword mute.
Crypto, take it back one more time just in case, because this was a really, really hard concept for me to like absorb. So I kind of want to take it back. So on the first one, right, we have our function greeter, the print the line, right? And we are passing the name crypto, but we set the name, the variable my name as that reference point, right? Crypto, right?
Yes.
And so now we are passing crypto into greeter on that second line. So there it's transferring ownership at that moment when I pass it on the greeter underneath the let name.
As soon as my name enters greeter here, it's done for.
Got it. So this reference point is just gone, right? So now on the other function on the other side, now we have the mutational, right, with the ampersand string, right? And that's the sign like that. That's for ampersand for me, it always means like it's referencing, right, instead of actually owning. Is that a fair statement?
Yeah. So an ampersand will always be a reference.
Got it. So now that we have the reference, I'm now kind of like having another copy. I know, like I'm doing reverse on my camera. It's like horrible for me. I look like the opposite of what I'm doing in the mirror. And so now it's now sending that reference over. And so therefore I can like this, I can replace this with Satoshi Nakamoto and then use that same reference to pass again. Yeah?
Close. There's a little bit more nuance.
Good.
So in greeter here, we're basically so references are pointers, right? You can think of them like that. So we're passing a pointer to my name into greeter instead of passing the actual pieces of memory that makes up my name.
Got it. Makes sense. Yeah. I know.
And then,
I'm just trying to share with everybody watching here because like I had to read that chapter and watch like a couple videos a few times for it to click. So hopefully that explanation kind of helps for everybody. But keep going, Crypto. Go for it.
So we have we can mutably reference my name. Or sorry, we can not reference, but we can mutate this value. And so you can have one mutable reference or an unlimited number of borrowed references. So we're going to use our mutable. So we're going to reassign my name to Satoshi Nakamoto and then pass the pointer back over to greeter. And my name will still be available afterwards. But I can't mutate again. All right, to control flow, I wrote this out by hand because who else loves handwritten beautiful things? So we have our if condition. So I went over this briefly in another window. So a keyword if, we have our condition that doesn't need to be in parentheses. The expression that will execute if the condition is true. And then else, we can execute another expression. We also have else if, but I just wanted to save a little room. We also have a few types of loops as well. So we can actually start an unlimited loop, but the Rust compiler will be upset if you don't break the loop. It'll error out, so make sure to include a case where it will break the loop. We have for loops too. So for I in blank.iter, so all loops need to be something called iterable. There are iterators in Rust, which are more compact versions of loops. They're kind of like the functional equivalent, so to speak. But if it's to be assigned on the right side of an expression, it needs to be iter. And usually to do that, you will call .iter on it. The other thing I'll note too is that if you say for I in 10, that won't work either. You have to create an iterator, and the way you'll do that is for I in 0.10. So the two dots actually represents a sequence, and so that will turn it into an iterator as well. Execute the expression inside the loop. And then we also have while loops as well. So a lot of other languages also has that. Okay, we have a nice little discussion about lifetimes here. So I didn't give you everything about references yet. This is the other really important caveat we should understand. The borrow checker ensures that references cannot point to memory that has already been freed, because that would be a catastrophic problem if it did. A lifetime refers to paths of execution of your program that a reference must remain valid for. So The reference cannot outlive the thing it refers to. Otherwise, you have created a memory sin called use after free. Using a lifetime is just asking the compiler to enforce the validity of the reference at runtime. All references, every single one, have distinct lifetimes, but sometimes it does not coincide cleanly with the scope. So this is really just for your mental modeling. You won't get too horribly into detail with this, but lifetimes can also be intermittently invalid before being reinitialized. In order to not run into compiler issues with a lifetime, we need to ensure that the referent, the place in memory we're referring to, is not dropped until we are fully done with this reference. And also, if you want to return your lifetime, do not forget to reinitialize it with let. If it went out of scope, that is. I drew a cool little diagram here. So we have our i32 in memory. We have our pointer. This pointer is of lifetime A, type i32, and it's called num. And so this here cannot be dropped before this is dropped on the right-hand side. Because if this is dropped, what are we actually referring to in memory? There's a bit of an issue there, of course.
I'm trying to get this concept down. Like, what's the best way to explain that one? Like, you're going down your code, right? It's compiling your code. You're referencing, like, you have all your variables. You've been using them. You have mutable. Then somehow you drop one, let's say one variable that, got transferred over, and then something's trying to reference it right after in the lower part of the code that is compiling. Is that what it's trying to protect you from?
Yes, exactly.
Yeah.
So let's say that you had a favorite restaurant in town, and you referenced it all the time, right?
Mm-hmm.
Hey, I love going to John's Pizzeria, right? But it would be really awkward if you referenced something that didn't exist, like God forbid it burnt down or got hit with a wrecking ball. Suddenly, the reference that you're using to point to John's Pizzeria, there's nothing that it actually refers to anymore.
Got it. Yeah, I'm thinking like at Church's Chicken when they get kind of crazy, and I'm feeling that midnight snack. I'm not, and then they got into a big fight, and then they closed it off. So like, yeah, it's just gone now. So like, it was there, and it technically it is there, but it's not available at that time. So maybe can it be available later, or is it just like gone until that runtime execution is just done?
So if the i32 is gone, there is big problems, and the lifetime basically says that I cannot drop this i32 before I drop num.
Got it.
Because otherwise, I cannot have an invalid reference.
Cool. All right. Don't go to Church's Chicken after midnight in Rust, y'all. That's it. Keep going, Crypto.
All right, and we are on our third to last slide here, and we are going to talk quite a bit more about structs, enums, traits, and generics. So I am kind of just jumbling these topics together because they are so interrelated and so important. So structs and enums could have attribute macros used on them. So it kind of looks like my drawing here. A really common attribute macro that is going to be commonly found in just about any Rust code base you see is debug. Basically, it makes it printable in printline. You'd be able to see it. We also have algebraic matching patterns for enums, so we're going to get into that pretty briefly with the next example. Associated methods that I mentioned earlier. I also mentioned trait. Yeah, we're just going to get into the examples. Talked about lifetimes. Yeah, okay, we're cool. So Rust is not an object-oriented programming language. It is imperative with functional features, and so we don't have things like classes. So the way we do things around here, so we'll define traits for types if there is a behavior that must be shared between them and associated methods. The important thing to understand in the with lifetimes is that if you want to use a reference inside of a struct or an enum, you need to explicitly annotate them. So we don't have what we would call lifetime elision here. Elision just means that the Rust compiler is smart enough to infer the lifetime of your references without you explicitly putting it there. And of course, when we don't want a single concrete type for our values, this is where generics enter the scene. This feature makes our type system a lot more flexible. And even in some places, we can have non-concrete types. And so we can basically say that, for example, we want to rely on a certain behavior, a certain trait. So we'll require that this trait implements, this generic implements this trait, so we can use this specified behavior inside of the function body. So you will actually see that really soon. Then we also have monadic error handling. So I mentioned this a lot earlier. I didn't want to get through this presentation without really talking more about it. But options are an enum with two options. Results in an enum with two options. You have OK, and then you have an error variant. And option can return you some or none. And you will actually wrap your responses using some of the associated methods. Okay, so I can't hold it any longer. We're going directly into the next example. So there is a good bit of boilerplate here, but keep in mind that in a lot of cases, you won't have to write out this whole boilerplate. There's really great libraries in Rust, like Anyhow for error handling. And actually, these type annotations are not even actually necessary, except for inside of the enum animals. So I'm using a pretty concrete example for you guys. So we have animals and we have a housefly. So we're associating some data with each of these enum variants inside of animals. So we have lifetime A, a string slice of lifetime A, and sounds. This is going to be associated data for every single variant of animals. And then for housefly, I structured it slightly different, but I just wanted to show the cool behaviors of traits that I could share the, where is it? I can share this trait called sound between all these types. Oh, there's our trait sound right over here. And so here's our different types of sounds. Dogs bark, cats meow, birds chirp, flies buzz, and then jellyfish don't make a sound. It's just a funny example. Here is an implementation of the animal error. The error implementation for animal error. So this is what the boilerplate actually looks like here. So impl animal error. So this will basically tell us how we are constructing our new error message here. Then display and error are the other important thing. So these two are traits that we are explicitly defining for animal error. And also, this is also a lifetime annotation, but it doesn't matter what lifetime it is, so we use the wildcard syntax. So that wildcard syntax is an underscore. The function associated with display to implement it for animal error is format, and it takes a reference to self in a formatter that we call f, immutable reference to such a formatter. And then we are going to write it we're going to write this data to the buffer with the write macro and return it as a result. So the write macro actually returns the exact result we're looking for very conveniently. Oh, another thing I forgot to mention, just real quick. Whenever you see in Rust that there isn't a semicolon, there isn't a semicolon here, it's actually an implicit return. So in Rust, we will not use return unless we're returning early from control flow. So if you're nested in a loop somewhere, nested in a matching statement, you should use return there. That's the only way you will cut off the control flow. But otherwise, if it's the end of the function, this will be an inferred return type. And then this is the implementation of error for animal error. So it takes a mutable reference to self. And then when I match against self, I can extract a type called string. And I will return no sound. So this is going to be the error variant and what I'm associating with it. Okay, here's the spicier piece. I'm going to implement this trait called sound for animals, and then I'm going to go ahead and implement sound for housefly. So in here, we're actually going to use our algebraic pattern matching. So I'm going to use match, and I'm going to match against self. And self just is the type that I'm using in this context, so that is animals. So I'm matching against self, which is of type animals. So what kind of animals we got? We got dogs, we got cats, we got birds, and then we have a wildcard for whatever else. But you guys know we only have 4 variants: dog, cat, bird, jellyfish. So whenever we get to the jellyfish variant, I'm going to return error. I'm going to create a new error message, animal error, and it's going to say animal makes no sound. An animal error is going to have its own static lifetime as well. So static just means it's going to live for the duration of the program. It's going to be inside of the binary, basically. So for each variant, I'm just printing it out and returning the sound it makes. So result has 2 different options. So whenever we use result, we need to cover both of them. So what happens when it's okay, we're just going to return sounds. And then when there's an error, we're going to return this type called animal error. And so okay is what corresponds to the left side, and then error is what corresponds to the right side here. So now we're going to implement sound for housefly. We're going to take ownership of self, kind of like I did here, and make sound. I'm going to print the name of the sound, and then I'm going to just return the sound. This is the constructor for housefly. I didn't make a constructor for the enums because I didn't really feel it was necessary. But for convenience, we can call housefly : new with a name and the sound it makes. And inside the main function, we'll talk a little bit more about this expression. So on the right-hand side here, this is another type of generic. It is heap allocated. It is a trait object. So traits are not sized. And sometimes we just want our return types to implement a certain trait for reliability reasons. Want to be able to always call a certain method on the return type, maybe. And so if we want to specify this type of behavior that, okay, I'm not just asking for one concrete type of error, I am asking for any types of errors that you might give me using boxed-in error. Dynamic also means it signifies something called dynamic dispatch, and it's a little bit slower than something like static dispatch in Rust. So we have our first variable, doggo. It is of type animals, and then we are instantiating a new one. So when we access variants inside of an enum again, we have our double colon syntax, the value, and then the associated values with dog. So in this case, it's a string slice, and then it is a value from the sounds enum. So here is one way we will handle our error variants. So make sound returns a result type. So we have to handle the result in some way, shape, or form. So one way you might do this, this is not really the good way of doing it, but it works. But it will crash your program if we return an error. And that is with .expect. And inside of expect, we just have a string literal that will return whatever message you specify. I'm going to make a housefly new. I'm going to call him buzzer, and he buzzes. So I'm going to call the same exact function on it and handle it a different way. So we know the housefly is always going to buzz, but just in case there's something weird going on, we can call unwrap. So unwrap by itself will actually crash your program if something goes wrong, but we have unwrap or else. Unwrap our default, and so we could actually calculate the value from a closure, which is kind of like an anonymous Lambda function, or we could actually just default return a value. So here's our jellyfish example. We're gonna create a new one. We're gonna call him Stinger, and he doesn't make a sound. All right, this time we're actually gonna crash the program. So we call make sound, and we're gonna use a question mark. So we can do this in the context of result to propagate any errors that bubble up beneath. So if your 6 libraries deep and it is very well written, a single question mark could return an accurate error from 4 libraries down. Error handling in Rust is a little bit complex. There are libraries like Anyhow that do make it a bit better. But one interesting challenge that a lot of beginners face is figuring out how to handle option enum and result enum. I have a little picture of a compiler here. So Fido says wolf, woof, buzzer says buzz, and then this is our error that has been propagated. Error, no sound, animal makes no sound. For anyone who wants to screw around with this example, this is the lengthiest one, so I actually just put it up in a gist on GitHub. But I do have one more example for you guys.
Crypto, can you paste that into chat so they can go directly to the link on there? Because I see it there, but there's no way to like copy and paste that. Can you copy and paste that into chat, or send it to me and I'll paste it down?
Yeah. Let me dig that up real quick.
Mm-hmm. It is a lot to swallow, guys, and honestly, in my experience with Rust, it's that first uphill battle of like getting the things to click, and you have to play with it. But having examples where somebody's like not the usual, like the Rustlings book or a couple of the videos, but just having someone explain that piece by piece has been like so awesome, especially having this opportunity to like get a few concepts in there, that everything that Crypto's covered, that it's like you see it live and then you can look at it, references with the code. It's super awesome. So definitely check out the gist on there. And Crypto, keep going.
Beautiful. Another note about trait objects. So they allow for values of different types. Types that implement a given trait could also be of different sizes. We can let the compiler derive a number of traits with the derived attribute. So I used derive debug in a couple of these different structs and enums. But yeah, it's super common. You're going to see that a lot, even in libraries like clap. So clap is the command line argument parser. You can actually write an entire command line application pretty much with derived macros, which is really cool. My preferred method, actually. Traits also can implement default methods. So let's briefly talk about that. So the way I structured the implementations of sound, we actually do not have a default implementation. So I only included the function signature, so result sounds animal error. But if I did include a default implementation and a type implements sound, then it will be able to use that default implementation. But in this case, I created specific implementations for specific types, namely animals and housefly. Oh, also, someone here might be wondering why is OK returning a tuple struct? I actually do not need to return a value at all from main, so I chose a tuple struct on the left-hand side of result. And if it goes off unhinged, that's all we want. Otherwise, it'll propagate an error for us. All right, and we have one last example here where I can talk a bit more about generics. We saw some lifetime annotations in the last example, so I'm going to use some generics here. So I do import from the standard library a type called error, and this is the trait that we implement for errors. So here we have a structure called generic struct. It derives 3 macros that really don't affect the implementation much, but I just wanted to show you guys some examples of derived macros. So I put in debug clone in default. Default will give us a default implementation of the structure. We can also implement it manually as well. Clone, we went over clone, but this is actually how you make something clonable. Oh yeah, we can talk about some trait bounds too. Very cool. So we have this function called generic function, and it has a trait bound where T must implement a type called clone. And this is because random var calls .clone. And so this would otherwise there'd be an error. The Rust compiler would be like, hey, you're missing a boundary here. One way in which you might not have to express this boundary in the same exact way, you could use a keyword called where right after the return type. So where t::clone, that's a little bit more of a cleaner way of doing it. And then the other way is if the lifetime has to be, not the lifetime, the implementation block requires clone. So you can do it at the high level there as well. Inside of main here, my generic struct, so we're just going to create a brand new one. Usually for structures, you would just create a constructor, which is called function new. It'll take your vector and spit out the generic struct. But you could also construct the type in this way as well. The colon question mark is basically if you don't implement format display, but it's just another way we can display data in console. Here we use call to generic function to return an option. We can actually print out options too. It's pretty cool. It comes out as some generic struct with the random list in it, so it's just wrapped inside of that some variant. Oh, here's a fun piece of syntax. I like this piece of syntax quite a bit. It's called if-let syntax. And so this is a different way of pattern matching in Rust. So the left-hand side is the pattern we're looking for, and the right-hand side is where we're getting the value to be compared from. So if this on the right-hand side evaluates to what is here specified on the left-hand side, we'll be able to execute this block of code right here, x.random_list, which would return a vector of u32s. Otherwise, we're just going to return an empty list, an empty vector of 3 values. So this is a demonstration of an iterator. So we can call iter on val. So val is a vector of u32. And iterators in Rust are also lazy. So iterators will not be consumed until you call something on it. In this case, we're using a method called map. And what map does is it calls the closure on every value passed to it through the iterator. And so as we're going through the collection, what we're doing is we're moving the value in. So this is what the keyword move does. This initiates the closure, the double pipes. So inside of it, we got num. And then we're taking num, and we're multiplying it by 3. And then while we do this, we're actually going to take the results, and we're going to wrap it up into a brand new vector. And when we print out this vector, we get 300, 600, and 900. Recall that the original values are 100, 200, 300. Oh, also, one other thing I'm going to mention while I have you guys. The standard library is fantastic. A vector is a heap allocated array that does not need to have a known size at compile time. So you can pop, push, and expand, contract. It's still going to take up the same address in memory. And so it's heap allocated. We don't need to know that at compile time. So this is another beautiful piece of the standard library. Closures, these anonymous functions, you'll see them very commonly with these high-level functional idioms that Rust has. So those are really cool and unique to explore. Not many languages really makes good use of functional components, so I always like to see people experimenting with them. Oh, also, map calls the closure on each element. Yeah. Yeah, okay, so this is actually all I got for you guys today. I'm super happy to take questions. If I missed anything in here.
No, it was good. Like, I think for me, you know, I would say as a major novice in Rust, there's a lot of concepts to absorb in this in general. Like, for me, my journey in Rust was like the Rustlings book or the book, right? And a couple Udemy classes. And I'm more of a visual learner, like kind of like what you were doing here, and then going step by step. And there's a lot of concepts for me to take in. And so, like, while I was doing the Udemy things, I would get stuck, and then I would read it in the Rustlings book, and then, oh, okay, that makes way more sense now that I have two different versions of it. And so now having like this other YouTube reference as well with all these examples, because sometimes for me, examples are like, okay, that's a great example of this very basic thing, but you didn't cover how this iteration works, right? And it's like literally in your examples right here, you have a lot of different fundamentals to connect with. So I think like being able to have this Rustlings, maybe some YouTube videos, you're going to be able to connect, you know, like connect the dots a little bit better with Rust. I think personally.
100%. And
Yeah.
I actually like that you bring up Rustlings because that is such a wonderful little course. It gets people in the habit of reading and writing Rust by debugging Rust code. So off the bat, you don't even have to worry about creating these cool, complex expressions. You can just fix up some code, get a better idea of how these mechanics are working before you go on to create your first starter project with Rust.
100%. Like, you know, it's nothing official yet, but I'm really trying to push a narrative for Developer DAO to have, like, I was going to say Rust Fridays, but we have too many things happening on Friday. So like Rust Thursdays, Rust Wednesdays, where we as a collaboration, like, build something with Rust, really simple, really basic. Maybe we rebuild Crypto's animal, you know, build and see if we can get it and understand it and get things moving. And now we have Crypto as a reference, super cool guy, always willing to help. So like if you're in Developer DAO, you see my VC5, say what's up, you know, he's hanging out. We're always hanging out, always really happy to help each other with issues that happen, you know. So much appreciated, Crypto. I mean, you're always dropping knowledges. Again, Crypto is part of Raisin Labs. He's basically the co-founder of Raisin Labs that's working out within the DAO. He's looking for contributors as well. And, you know, we're just hanging out. Crypto, I think, are you for hire? Are you available, or are you got something going on?
I'm kind of on the fence. I don't want to go through 4 to 6 interview rounds again and waste massive time with these employers in Web3. Yeah, I mean, Web3 is not friendly to juniors. I'll say that much. And even if you've built up a substantial knowledge like me, you could still just not even get an interview. So I'm much happier to take on like advisory work or consulting work.
Got it. So you heard it here, folks. You know, if you're looking for some advisor help, Crypto's around. Really dope in Solidity, Rust. So definitely hit him up, get to know him, and hopefully it's not so scary with Rust. I know there was a lot of terms to get in there, but like, I'm around, I'm learning. Ask me, I'll help you with what I can. But when in doubt, Crypto's the guy I'm going to go to anyway. So if you're in Developer DAO, you know, you'll see him around. He's always around in the socials. So thank you again so much, Crypto. And hopefully you guys got a good chunk of Rust out of this.
Hell yeah. Thank you so much for having me here, Billy, today. And one more message for the folks out at home. Frustration is part of the journey with Rust. If you're not getting frustrated, you're not trying hard enough. And thank you so much for being here.
All right, guys. Oh, again, next week we are having a community workshop with Dappa Dan. It's going to be a technical writing workshop of how to, get good, get paid. But it is on a special day. It is going to be on a Thursday because Friday didn't work out. So again, just a reminder for Thursday, we're going to make a little bit of noise for that. So it's going to be Thursday instead of Friday next week. And hopefully see you guys there. Catch you guys later.
Peace.
See you.